Welcome to learning about insertion sort. So, what exactly is insertion sort? It's a sequential method to sort unordered data. For example, let's take an array of random integers that I came up with. As you can see, 12 is less than 21, 21 is greater than 17, 17 is greater than 10, 10 is less than 31, there's no sequential order. What we want to do is order this in such a way that the values on the left are smaller than the values on the right. So if we ordered this list in general, you will see that 10 is less than 12, 12 is less than 15, 15 is less than 17, all the way through the list. That is our sequential order, smaller values on the left, greater values on the right. So, how do I actually use insertion sort? Well, it's easier than you might think. Let's first take an unordered array. We'll just use one with 4 elements to make it easier. You'll see that 21 is greater than 12, 12 is less than 17, and 17 is greater than 10. Let's take a look at the first 2 elements, 21 and 12. You notice that 12 is less than 21, so we swap 12 and 21, and then we insert 12 into our subarray, denoted in green. Now we take a look at the next 2 elements, 21 and 17. Once again, we'll notice that 17 is less than 21. So we swap 17 and 21, and we insert 17 into the subarray. So now in the subarray, we have 12 and 17 sequentially in order, and then outside we have 21 and 10, which still are not in sequential order. So we take a look at the next 2 elements, 21 and 10. We notice that 10 is less than 21. Once again, we swap, but oh no. Now, within the subarray, we have an unordered list, which is a problem. So in order to remedy this, only inside of the ordered array, we will swap 10 with 17. Okay, so now that we swapped 10 and 17, 17 is in the correct place, 10 is less than 17, but 10 is still less than 12. So we have to perform another swap. So now that 10 is less than 12, 12 is less than 17, our subarray is now in order, and we can continue by checking the final element, which is 21. Boom. We add that to our ordered array. 10 is less than 12, 12 is less than 17, 17 is less than 21, sequential order using insert sort. So let's get to those nitty-gritty details, starting with time complexity. With the worst case, say, we'll use a reverse ordering of a list. The sequential order in this case is still there, but it's in reverse. What we want to do, like I've mentioned before, is make 10 the value on the left and 30 the value on the right. So we have to swap 20 and 30, but then we have to move 10 over 2 places. So 10 is less than 30, swap, 10 is less than 20, swap, and then you'll end up with 10, 20, 30. But at the most, we'll be traversing the array twice, which is O(n squared). For the average case, we'll use a partially ordered list. As you can see, 10 is less than 30, but 30 is greater than 20. So we only have to perform one swap, but we still traverse the array twice, as we will still have to access the subarray. That is still O(n squared). The best case scenario is a pre-ordered list that is already in sequential order. So as you can see, 10 is less than 20, 20 is less than 30. Perfect. We don't have to access the subarray. This becomes the fully sequentially ordered list. So we traverse the array once, that's O of n. Wonderful. So now let's talk about stability. Is it stable or is it unstable? Well, it's stable by nature. And this has to do with the fact that even with duplicate keys, order will be maintained in the output array as well as the input array. And here's an example. The first 4 integers in the array are the unordered array, and then the second one is going to be our ordered array. You'll notice that no matter what happens, the 20 in green will always be before the 20 in orange. Pre-ordered and post-ordered, and that is special. That's what makes it stable. And this is determined by the fact that the element A of J comes before the element A of I, if and only if the element A J is less than the element A of I. Because 20 is equal to 20, no matter what, the leftmost element will come first, and then the rightmost. So even if there were numbers in between, say there was 30, 20, 15, 20, 10, no matter what, that first 20 will always be on the left of the one on the right. Green will become before orange. Stability achieved. But now, is it in place? Of course it is, even though it sounds a little counterintuitive. I want you to think of the array as having a subarray, which is the sorted portion before the sorted array, or the unsorted array, my apologies. So here's an example. We have a completely unordered array. I'll denote the unordered parts in orange and the ordered parts in green. So let's perform 4 iterations of insertion sort. We'll see that 10 is less than 20, 20 equal to 20 still comes before the other one, and then 20 is less than 30, which gives us 15 and 5 still unordered. Notice how we never physically made another array. All we've done is swapped the elements inside of the array according to the fact that they're less than the one ahead of them. So in this array, we have 4 elements that are sorted and 2 elements that are unsorted. If we performed 1 iteration, we would have 1 element that is sorted and 5 that are unsorted. With 2 iterations, we'd have 2 that are sorted, 4 that are unsorted. Then we'd have 3 and 3, 4 and 2, 5 and 1, and then finally a completely sorted array with 0 unsorted values. No matter what happens, we are not creating another array in order to store these values, so we are not using any extra memory, and that makes it in place. And with that, I'll thank you for watching.